Hello friends, welcome back to my channel. This is 14th part of my discussion on liquid extraction, and I will continue discussing stage-wise liquid extraction with insoluble liquids. In my previous video, that is in part 13, I have discussed the theoretical aspect of single stage liquid extraction with insoluble liquids. And today in part number 14, I will be discussing a numerical that is based on single stage liquid extraction with insoluble liquids. I am giving link to the playlist which has all of my videos on liquid extraction. The link is available in the description section. You please watch all relevant videos on liquid extraction. So let us begin today's discussion. Okay. So first of all, let us look at the numerical statement. Nicotine is to be extracted from its solution with water. The solution is containing 1% weight of nicotine. The extraction is carried out at 20 degrees Celsius using kerosene as the extracting solvent. The quantity of feed is 150 kg and it is extracted once using 200 kg of solvent. Find the percentage extraction for this extraction task. Here in this case, water and kerosene, they are essentially insoluble in each other. Then the equilibrium data is given to us. The data is for kg nicotine per kg water. You have different values for this quantity, and then you have values for kg nicotine per kg kerosene. So corresponding values of these two quantities, they are in equilibrium with each other. So this is the equilibrium data. So in this case, the system is you have water plus nicotine solution, that is the feed solution. So in this case, water is A and nicotine is C, the solute to be recovered nicotine, and the extracting solvent that is being used, it is kerosene, that is P. And it is said that A and B, that is water and kerosene, they are essentially insoluble in each other. So this information is provided to us. Essentially insoluble with each other. Okay. The other information is the feed solution is to be extracted once. That means it is a single stage operation. It is a single stage operation. That means the extraction operation, it is to be carried out in a single stage. And we are supposed to find out percentage extraction. How much of the nicotine that is present in the feed solution, it gets extracted in the process. We have to report this in percentage. So let us start the solution. Let us solve this problem. First of all, we will list the given data. The feed solution, it is a solution of nicotine and water. As I said, nicotine in this case is C and water is E. Then the quantity of feed is given to us. It is 150 kg. The feed is containing 1% of nicotine in it. That is 1% C in it, which means that XF, that is weight fraction, 1% on weight basis, 1 weight % of nicotine. The feed is containing 1 weight % of nicotine. So that will be converted to weight fraction by dividing it with 100. So XF will be 1 upon 100, that is 0.01. Small XF, weight fraction of nicotine in the feed. Then the operation to be used is single stage liquid extraction. And A and B, that is water and kerosene, they are insoluble in each other. The solvent to be used is pure kerosene. The meaning is that it is not having any nicotine in it. Therefore, Ys is equal to 0. And the quantity of solvent to be used, it is given to us. It is S10. It is 200 kg. And this kerosene and water, they are immiscible in each other. They are essentially insoluble in each other. So we can use the ternary diagram, or we can plot the ternary equilibria in terms of capital X and capital Y. That is weight fraction of nicotine on a nicotine-free basis. Then the equilibrium data is given to us. We have different values of kg nicotine per kg water and kg nicotine per kg kerosene that are in equilibrium with each other. These values are in equilibrium with each other. This data is given to us. Now, if you look at this ratio, kg nicotine per kg water in the raffinate, the kg nicotine per kg water is weight fraction of nicotine on nicotine-free basis in the raffinate, because the weight fraction is expressed on nicotine-free basis. In the denominator, there is no consideration of nicotine. So it is kg nicotine per kg water, which is nothing but weight fraction of nicotine on nicotine-free basis in the raffinate. And that is nothing but capital X. I have discussed about it in my earlier videos. You please watch those videos if you have not yet seen those videos. So kg nicotine per kg water is nothing but capital X. The other quantity is kg nicotine per kg kerosene, which is nothing but weight fraction of nicotine on nicotine-free basis in the extract. And this is nothing but capital Y. So in other words, we have values of X and Y that are in equilibrium with each other. The equilibrium data is given in terms of X and Y. You have different values of X in equilibrium with different values of Y. So equilibrium data is directly given to us in terms of capital X and capital Y. So there is no need of doing any conversion in this case. You have values of X and Y directly given to us, and we can use them for plotting the graph. Then what are we supposed to find? What to find? We have to find out percentage extraction of nicotine in single stage operation. The task is to find out percentage extraction of nicotine. How much of the nicotine gets extracted? So that is what we have to report. So let us start the solution. First of all, we will have to find capital X and capital XF and capital YS. What are given to us? They have given small xf and small ys. So first task is we will convert this to capital XF and capital ys. How are you going to convert that? How are you going to get XF? XF will be small xf divided by 1 minus small xf. I have discussed this relationship in part number 30 in my lecture series on liquid extraction. So capital XF is small xf divided by 1 minus small xf. Small xf is 0.01, that is given to us. Therefore, capital XF will be 0.01 divided by 1 minus 0.01. That gives us XF as 0.101. Then we have to calculate capital YS. Capital YS is small ys divided by 1 minus small ys. But small ys is 0. Therefore, capital YS will be 0 upon 1 minus 0. That is, capital YS comes out to be 0. So that ends step number 1. We have got the values for capital XFI, capital YS. Now let us get quantities of A and B. Quantity of A in the feed and quantity of B in the solvent. Because all of the A that we will be getting in this step, it will go to the raffinate phase, and all of the B, it will be going to the extract phase, because in this case A and B, they are insoluble in each other. B will not go to the raffinate phase, A will not go to the extract phase. So let us first we will calculate quantity of A. So A is that part of the feed other than C. So if XF is weight fraction of C, 1 minus XF would be the weight fraction of A in it. So simply quantity of A will be quantity of feed into 1 minus XF. And F is given to us, it is 150 kg. XF is also known to us, it is 0.01. Therefore, A will be 150 into 1 minus 0.01. Small xf. Again, you please understand here we have to use weight fraction. Therefore, A will be equal to this will give us A as 148.5 kg. Then we have to calculate the quantity of B that is present in the solvent, because the same quantity will come into the extract phase. So it will be B into S. B is equal to S10 into 1 minus Ys, because Ys is the solute. Ys weight fraction is solute. The remaining would be B in it. But Ys is 0. Therefore, S10 is 200 kg and Ys is 0. That gives us B is equal to 200 into 1 minus 0. That gives us B as 200 kg. So in this way, we have got values of A and values of A and B, quantities of A and B. A is 148.5 kg and B is 200 kg. Now next we will, since we need to plot the operating line, and we can do that by using the slope of the operating line. So first of all, we will have to find out the slope of the operating line. The slope of the operating line is, for this operation, slope is given as minus A upon B. So I have discussed this in my previous video. You please watch it. Then we know the values of A and B. So A is 148.5 kg, B is 200 kg. Therefore, slope will be minus 148.5 divided by 200. That is, slope will be equal to minus 0.74. Slope will be minus 0.74. So in this way, we get the slope of the operating line. We will be using it in our, we will be using it for plotting the operating line. Okay, now next step is we will be plotting the graph. And for plotting the graph, I have used same scales on both the axes. So on x-axis, we are plotting capital X, and on y-axis, we are plotting capital Y. So if you plot the given data, you'll be getting a curve, which is the equilibrium curve. So after plotting the graph, we need to plot the operating line. Endpoints for this operating line. One endpoint is XFY, capital Ys, capital XF, capital Ys. Both are known to us. That means we can fix the operating line at this end. And then we will draw the line of the required slope to get the other endpoint. What is the other endpoint? X1, Y1. This is the point at which the operating line intersects the equilibrium curve. So endpoints of the operating line are XFYS and X1, Y1, and slope we just found out, it is minus 0.74. So the angle made by the line with the horizontal would be tan inverse of minus 0.74. It would be tan inverse of minus 0.74. and that comes out to be minus 36.4 degree. Okay, so we need to plot a line with this slope, or which makes an angle of minus 36.4. The angle, this is the horizon key, and since this line is of negative slope, so this angle is theta. Then slope of this line is tan theta, slope of the line is tan theta. Now in our case, since the angle made by the operating line with the horizontal is minus 36, so we are going to measure the angle in this way. And this angle is 36.4 degree. So since you are measuring it in this direction, it is minus 36.4. So a line drawn with an angle of 36.4 with the horizontal in this way would be the desired operating line. So slope will be minus 0.74. Okay, so the task is to plot this operating line. So we will do that. What I will do in order to plot, now my aim is to plot a operating line which is making an where this angle is 36.4 degree. Okay, so what I will do, I will use the definition of tan theta. So this is theta. So for this particular right angle triangle, how will you define tan theta? Tan theta will be equal to the opposite side. Let us say it is m divided by adjacent side. Let us say it is n. So it is m upon n. This is the slope. So I can say that slope is equal to m upon n. And if I make n as 1, if n is equal to 1, then slope will be equal to n. So I am going to use this concept for plotting the operating line. That is, I will make the horizontal distance equal to 1, and then the vertical, if that is done, the vertical distance will be nothing but a value that is equal to the slope minus 0.74. Okay, so I'll tell you how to do that. So I'm going to use the definition of slope for plotting the operating line, or you can measure an angle of 30. It is 36.5. Sorry, 36.5. So you can measure an angle of 36.5 degree angle with the horizontal in this direction. You'll be measuring it in a clockwise direction. So that will give you a line with negative slope, because the slope of the operating line is negative. Okay, so let me do it. I'll tell you. So let me first erase it, because I'm going to show you on the graph itself. So I'll just erase it. Just a minute. So we are now going to plot the operating line of desired slope. Let me first erase it so that I can show you the other things. So first we will locate the point that is known to us, the point whose coordinates are known. That is xf,ys, point with coordinates of xf,ys. In this case, xf is 0.0101 and ys is 0. So that means the point will be located on the x-axis, where x is 0.01. 0.0101. So 0.0101 is 0.0101 is over here. Now the operating line will start at this point and it will be of a negative slope. So I will travel 1 unit. This is 1 unit. Okay, so I'll travel as per my discussion because I'll be using the definition of theta, definition of the slope. So this I'll travel 1 unit distance. If I travel 1 unit distance on the left side, why on the left side? Because we have to plot a line of negative slope. So if I do that, the distance of 1 unit will be till this point. Again, you please remember, you can use this approach if you are using the same scale on both the axes. So on y-axis, 1 centimeter is 0.005 on the x-axis, and on the y-axis also the same scale is used. So if that is the case, then and then only you can use this approach. Otherwise, you can plot the angle. Plot the operating line by using the angle made by it with the horizontal. So I have traveled 1 unit. Now I have to travel a distance in the vertical direction, which is equal to the slope of the operating line, and slope is minus 0.74. Slope is minus 0.74. So I will have to travel a distance of 0.74 in the vertical direction. So I started with the given point. I traveled 1 unit on the left side. Why on the left side? Because I want to have a line of negative slope, and then I will have to travel a vertical distance that is equal to the slope. So that gives me, so this is 0.2, 0.4, 0.6, 0.7 and 0.74. So I get this point. So my operating line will be passing through this point and this point. So when I draw this line, I will extend it so that it intersects the equilibrium curve. So in this case, this angle is 36.5 degree. This angle is 36.5 degree. So the angle measured in clockwise direction. Are you understanding it? So in this way, you can plot the operating line. Now once I do that, I get the intersection point. Let me erase it because. So then I get this intersection point, and I will read the coordinate. X coordinate of this point will give me x1, and y coordinate of this point will give me y1. So in this case, x1 comes out to be 0.0045. You can check. So this is 0.004. This will be 0.0045, and y1 in this case is 0.0041. So it is 0.0041. So that was my objective. After plotting the operating curve, I have got the values of x1 and y1. Now I will use these values for calculating percentage extraction. So I hope you have learned how to plot the operating line, how to plot the operating line of desired slope. Now let us find out percentage extraction. So percentage extraction, we just got values of x1 and y1. x1 is 0.0045 and capital Y1 is 0.0041. Now unextracted nicotine, let me denote it as C raffinate. Unextracted nicotine will remain in the raffinate phase. So can I get the quantity of nicotine in the raffinate phase? Yes, I can. And how? Let us understand. Let me denote the quantity of nicotine in the raffinate as C raffinate. For that, I will be using the value of x1, that is octet. So x1 is 0.0045. So it is kg nicotine per kg of water. So if I have to get kg nicotine, I will multiply, if I multiply with kg water, I will have to multiply with kg of water, that is A. So if I do that, I will get kg of nicotine in the raffinate, which is unextracted nicotine. So C raffinate, that is nicotine in the raffinate, which is unextracted nicotine, it will be obtained by multiplying X1 with E. How? In this way, per kg it is 0.045. So in the given kgs of A, what will be the amount of nicotine? So we can obtain it in this way. So C raffinate is equal to X1 into A, that is C raffinate is equal to 0.0045 into 148.5. That gives me C raffinate as 0.668 kg. So 0.668 kg nicotine is in the raffinate, and this is unextracted nicotine. Then let us find, we know nicotine in the feed. Let me denote it as C in feed. So C in feed will be weight fraction of C in feed into total feed. So therefore C in feed will be equal to 0.01 into 150. That is C in feed will be 1.5 kg. So out of 1.5 kg, 0.668 kg remains unextracted. So 1.5 minus 0.668, it will be the amount of the percentage extraction of, or the kg of nicotine that is in the extract phase, or kg of nicotine that is extracted. So now we can find percentage extraction. So percentage extraction is equal to C in feed, that is nicotine in feed minus nicotine in raffinate, is equal to nicotine in extract divided by nicotine in feed into 100. So therefore percentage extraction, let me erase it. So percentage extraction, it will be 1.5 because C in feed is 1.5 and C in raffinate is 0.668 divided by 1.5 into 100. That is percentage extraction comes out to be 55.47, and that is the final answer that we have to report in this case. Now we are reporting percentage extraction of nicotine in a single stage operation. So in this way, you have to solve the numericals that involve extraction with insoluble liquids. So ultimately, we are reporting percentage extraction that is obtained in single stage operation. So with this, I end my discussion for this numerical. Here I have told you how to solve a numerical that is based on single stage extraction with insoluble liquids. In my next video, I will be discussing multi-stage cross-current liquid extraction involving insoluble liquids, and then I'll be solving one numerical based on that topic. For now, let me end my discussion. Thanks for watching my video. I hope you have learned something. If you have any doubts, you please mention them in the comment section. I'm eagerly waiting for your feedback. You can give that in the comment section. Thanks for watching this video. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. And do hit the like button if you really like my video. Thank you and have a nice day. Bye bye. Hope to see you soon in my next video.